The sun has been particularly strong in recent times, and it's about to undergo a pivotal and captivating change: the reversal of its magnetic field. This reversal happens roughly at the midpoint of the solar cycle and has far-reaching implications for Earth. In fact, the sun could soon pose a significant threat that might cause serious disruption and chaos for all of humanity. The sun's magnetic field is generated by the movement of electrically charged gases in its interior, a process known as the solar dynamo. Over time, this magnetic field grows in intensity and becomes more complex due to the sun's rotation and convective movements. Eventually, this leads to a total reversal of the magnetic poles, where the north magnetic pole becomes the south magnetic pole, and vice versa. Let's break down the entire process by taking a closer look at the sun. The sun is primarily made up of hydrogen and helium in the form of plasma, a state of matter where electrons are not bound to atoms, creating a mix of free electrons and ions. The sun's interior consists of several layers, with the core at the center surrounded by the radiative and convective zones. The core is where nuclear fusion occurs, converting hydrogen into helium and releasing enormous amounts of energy. Surrounding the core is the radiative zone, where energy is transferred outward through radiation. Here, energy moves very slowly as photons are absorbed and re-emitted by the solar plasma. The outermost layer of the sun's interior is the convective zone, where energy is transported by convection. Hot plasma rises to the surface, cools and sinks again, creating convective currents. The solar dynamo process primarily occurs in the convective zone and the tachocline, a thin layer between the radiative and convective zones. This region is crucial because the sun's differential rotation and shear flows play a key role in generating the magnetic field. Interestingly, the sun doesn't rotate as a solid body. Different parts of it rotate at different rates, with the equator spinning faster than the poles, a phenomenon known as differential rotation. This stretches and twists the magnetic field lines, amplifying the sun's magnetic field. The solar cycle is an approximately 11-year cycle during which the sun's magnetic field undergoes a series of changes, culminating in a reversal of its poles. This cycle is driven by the solar dynamo and consists of several phases. At the beginning of the solar cycle, the sun is in a phase known as solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is relatively simple, with a clear north and south magnetic pole. As the cycle progresses, the number of sunspots increases. Sunspots are regions of intense magnetic activity, and are associated with the rising magnetic activity from the sun's interior. These sunspots appear in pairs with opposite magnetic polarities and gradually move toward the equator. Around the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity with the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. The magnetic field becomes extremely complex and tangled due to the constant rotation and shearing caused by differential rotation and convection. As solar maximum fades, the magnetic field begins to reconfigure itself. The twisted and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses. The north magnetic pole becomes the south magnetic pole, and vice versa. This process is facilitated by the movement and realignment of plasma regions. After the magnetic reversal, the sun enters a phase of declining activity, returning to solar minimum, and eventually the cycle is ready to begin again. Currently, we are in the solar maximum phase, and the sun's magnetic field is about to flip. During this stage, we can expect some dramatic solar activity that could be as dangerous as it is captivating. However, the sun's magnetic field reversal is not an abrupt flip but a gradual process. As the solar cycle progresses, the sun's magnetic field undergoes a series of changes, and when the field is at its most twisted and tangled state, it reaches a tipping point and begins to reorganize itself, leading to a flip. So, when will the sun's magnetic field reverse? Scientists monitor the sun's magnetic activity using various instruments and techniques. Observatories equipped with powerful solar telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, measure the sun's magnetic field and its changes over time. One key indicator of an impending magnetic reversal is the behavior of sunspots during solar maximum. Sunspots become more frequent and move toward the sun's equator, signaling that the magnetic field is becoming more unstable and preparing to flip. Let's dive a bit deeper into sunspots. When the sun's magnetic field lines become stretched and tangled due to differential rotation, they loop above the sun's surface, suppressing the convective flow of hot plasma from the sun's interior. This results in cooler, darker patches on the sun's surface, which are observed as sunspots. Sunspots are not only fascinating solar features, they can also produce intense solar flares and CMEs. These phenomena release vast amounts of energy and charged particles into space, and when directed toward Earth, they can disrupt satellite communications, affect power grids, and pose risks to astronauts in space. Additionally, increased solar activity can enhance auroras but also raise radiation levels in Earth's upper atmosphere. While we're on the topic, it's essential to understand the difference between solar flares and coronal mass ejections, CMEs. Both are powerful bursts of energy from the sun, but they differ in several ways. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They emit a significant amount of energy and light, often in the form of X-rays and ultraviolet radiation. Think of them as a burst of bright light and heat on the sun's surface, like a massive explosion. On the other hand, CMEs are massive eruptions of solar wind and magnetic fields from the solar corona. They can be thought of as giant bubbles of gas and magnetic fields ejected into space. While a solar flare doesn't necessarily cause a CME, they can sometimes be linked. A particularly powerful solar flare may be accompanied by a CME, but they are distinct phenomena. In terms of danger, it depends on what we're discussing. Solar flares can disrupt radio communications, GPS signals, and pose a significant risk to astronauts due to intense radiation. CMEs, however, can have a broader impact. They can cause geomagnetic storms that disrupt power systems, satellite operations, and create stunning auroras. They can also increase radiation in Earth's atmosphere. During times of high solar activity, the amount of radiation reaching Earth also increases. Satellites and other space vehicles are particularly vulnerable to heightened solar activity. The charged particles from the sun can damage electronic components, disrupt communication signals, and even alter satellite orbits. In addition to damaging technology and infrastructure, increased solar activity can have other effects on the planet. While the sun's magnetic field reversal doesn't directly affect Earth's climate, the associated changes in solar activity can have ripple effects. Some studies suggest that shifts in solar activity can influence weather patterns, although this is still an area of ongoing research. Solar radiation can influence climatic conditions and weather patterns. For example, increased solar activity can slightly warm Earth's atmosphere, potentially intensifying existing climate change. While auroras are one of the more awe-inspiring effects we experience on Earth, they are not the only consequence of heightened solar activity. Auroras, commonly known as the northern and southern lights, are stunning natural light displays caused when charged particles from the sun interact with Earth's magnetic field and atmosphere. These lights can also be seen near the South Pole, and during periods of high solar activity, auroras become more frequent and visible at lower latitudes, creating spectacular night shows. However, beyond the beautiful auroras, there are also concerning aspects of the sun's magnetic activity that could lead to global disruption if we are unprepared. One of the most significant risks associated with a solar magnetic field reversal is the increased likelihood of geomagnetic storms. These storms occur when solar winds laden with charged particles collide with Earth's magnetic field. In extreme cases, geomagnetic storms can cause widespread power outages and damage infrastructure. A historic example of this is the Carrington event on September 1, 1859. On that morning, astronomer Richard Carrington observed a bright white flare from a group of sunspots. This marked the beginning of the largest recorded geomagnetic storm. The flare, caused by a massive release of magnetic energy, unleashed a coronal mass ejection (CME) that traveled at a remarkable speed of over 2 million miles per hour, reaching Earth in just 17.6 hours. Upon its arrival, The CME triggered a geomagnetic storm that immediately disrupted Earth's magnetic field, sending currents through the ground and causing severe interference with telegraph lines, the primary communication system of the time. Sparks flew from telegraph machines, operators received electric shocks, and some telegraph stations even caught fire. In some instances, the induced currents were so strong that telegraph operators could send and receive messages without batteries. The Carrington event also produced some of the most magnificent auroras ever recorded. These auroras were visible far beyond their usual polar regions, with sightings reported as far south as the Caribbean, Mexico, and Hawaii. In the northeastern U.S., the auroras were so bright that people could read newspapers by their light. In the Rocky Mountains, gold miners were awakened by the glow, mistaking it for dawn. The sky was described as ablaze with red, green, and purple hues, dancing across the horizon. If a solar storm of this magnitude were to strike Earth today, the consequences would be devastating. The Sun is currently undergoing significant changes, including the reversal of its magnetic field, a phenomenon that occurs approximately every 11 years as part of the solar cycle. This event, driven by the solar dynamo, has wide-reaching implications for Earth, potentially causing disruption and catastrophe. The Sun's magnetic field is generated by the movement of electrically charged gases in its interior, resulting in a complex magnetic field that periodically reverses. The Sun is primarily composed of hydrogen and helium plasma, with energy produced by nuclear fusion in its core. This energy moves outward through the radiative zone and is then transferred by convection in the outer layers. The solar dynamo system, which operates in the convective zone and the tachocline, produces the Sun's magnetic field. Differential rotation, where the equator rotates faster than the poles, stretches and intensifies magnetic field lines, driving the solar cycle. Currently, the Sun is in its solar maximum phase, where sunspots and solar activity are at their peak, heightening the potential risks of solar flares and CMEs, which can disrupt satellite communications, power grids, and pose dangers to astronauts. Scientists closely monitor the Sun's magnetic activity and sunspot behavior to predict the timing of these magnetic field reversals. Sunspots, caused by tangled magnetic lines, can generate solar flares and CMEs, both powerful emissions of energy that impact Earth in different ways. While solar flares release radiation, CMEs eject massive amounts of solar particles into space. These phenomena not only enhance auroras but also pose serious threats to Earth's technology and infrastructure. The Sun's behavior is a fascinating interplay of physics and natural phenomena, influencing not just our solar system but life on Earth as well. Understanding the complexities of solar activity is crucial, especially as we continue to rely on technology that can be affected by solar events. The Sun produces energy through nuclear fusion, converting hydrogen into helium and releasing immense amounts of energy in the process. This energy travels through various layers of the Sun before reaching its surface and radiating into space. Solar activity manifests in many forms, including sunspots, solar flares, and coronal mass ejections. Sunspots are cooler areas on the Sun's surface caused by magnetic activity, appearing as dark spots. These changes in solar activity follow an approximately 11-year cycle, known as the solar cycle, where periods of high activity, solar maximum, are followed by calmer periods, solar minimum. During solar maximum, the number of sunspots increases. Solar flares are sudden bursts of energy that release radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These intense bursts can affect radio communications and pose risks to astronauts in space. CMEs, on the other hand, are massive ejections of solar wind and magnetic fields that rise above the solar corona or are released into space. When directed toward Earth, these ejections can cause geomagnetic storms that disrupt the planet's magnetic field, resulting in beautiful auroras but also potential technological disruptions. The impacts of solar activity extend beyond space. They influence Earth's atmosphere and surface. Studies suggest that variations in solar radiation can affect climate patterns, potentially contributing to weather anomalies. Increased solar activity can also lead to atmospheric warming, which is an important factor in discussions about climate change. Furthermore, The potential for technological disruption due to solar storms cannot be underestimated. A severe geomagnetic storm could damage electrical grids, disrupt satellite operations, and affect navigation systems. Preparing for such events involves monitoring solar activity and developing strategies to mitigate their effects on infrastructure. Scientists continue to study the sun's magnetic field and its cycles to better predict when major solar events might occur. This research involves a combination of ground-based and space-based observatories that track sunspots, measure magnetic fields, and analyze solar wind. With advancing technology, our ability to forecast solar activity improves, which is critical for protecting our technological systems and ensuring the safety of astronauts. As we learn more about the sun, its impact on Earth becomes increasingly clear. From the dazzling displays of auroras to the potential challenges posed by solar storms, the sun remains a powerful force in our solar system. Understanding its cycles and behaviors not only deepens our knowledge of astronomy but also enhances our preparedness for the effects of solar activity on modern life.